Earlier this chapter we talked about water being amphoteric, that it can act as either an acid or as a base. So if we take a closer look at water, if we had a sample of liquid water, one water molecule could act as an acid and another one could act as a base. It doesn't matter which one you write where. We have an acid donating and a base accepting. This reaction is not going to be 100%. It's less than 100%. So when we write the products, we'll have this equilibrium set of arrows. The water that accepted an extra H is now going to have the formula H3O+. That's the hydronium ion. And we can write the phase. That would be in water, so it would be aqueous. The water that donated that H+, lost one H and it lost a positive 1 charge, so it turns into the hydroxide anion. This is called the self-ionization of water. And if you measure this at the normal temperature in the lab, 25 degrees Celsius, what you find is the concentration of hydronium is a very small number, 1 times 10 to the negative 7 molar. That's also the concentration of the hydroxide, because when these are made, they're made in a 1-to-1 ratio. So if we make this number for hydronium, we have to make the same amount of hydroxide. We're going to use this in what's called the ion product of water. The ion product of water has the symbol capital K and then a subscript W. The W stands for water. And Kw is concentration of hydronium times the concentration of hydroxide. And if we plug in the numbers, 1 times 10 to the negative 7 for the hydronium and 1 times 10 to the negative 7 for the hydroxide, we multiply those two together, we get 1 times 10 to the negative 14. So Kw tells you something about how much water is acting as an acid, how much is acting as a base. It's a very small amount. This Kw, 10 to the negative 14, is a constant. As long as the temperature doesn't change, that number will not change. When you put an acid into water, the acid makes hydronium, and the concentration of hydronium will increase. An acidic solution is a solution where you have more hydronium than hydroxide. When the hydronium goes up, the hydroxide goes down. In pure water, these two are equal to each other. But in an acidic solution, we'll have more hydronium than hydroxide. And in a basic solution, it's just the opposite. A basic solution, when you add a base to water, you make more hydroxide. So the hydroxide goes up, and the concentration of hydronium goes down. So you end up with more hydroxide than hydronium. An acidic solution has more hydronium. A basic solution has more hydroxide. And when they're equal to each other in pure water, this would be neither acidic nor basic. This would be a neutral solution.